There may be times that we are asked to graph the solution set of an inequality that involves a rational expression that's a polynomial divided by a polynomial. When we are asked to do this, we can deal with this a little bit like we did with the quadratic inequalities. One of the first steps that's really important to do is to make sure you have the entire expression on one side and then your inequality and 0 on the other side. If there's other variable terms on the other side when you start, you want to bring them over with the rest of the variable terms and then make sure you build and get common denominators so that you have that rational expression, the inequality, and then 0. And remember from the previous segment that it's important to have a 0 on the other side of the inequality when I'm dealing with quadratic or rational expressions with an inequality, because 0 is that cutoff between the numbers that are positive values and the numbers that are negative values. And so if I could just write this rational expression in terms of products and quotients, it's very easy for me to say whether a product or a quotient overall will be a number that's positive or negative, and that kind of leads us into an easier way of getting these solution sets. So the first thing we want to do then is once we see that our inequality it has with respect to having our 0 on the other side, then I want to factor anything that I can on the side that involves the variable expression. Now the numerator x squared minus 5x plus 6 does factor. It's a trinomial. There are no common factors all the way through. It's in descending order. The lead coefficient is 1. And the factors of positive 6 that add to get negative 5 are negative 2 and negative 3. So my numerator factors as x minus 2 times x minus 3. And that's all over. My denominator doesn't factor any further. There's no common factors all the way through, and my x is to the first power. So that denominator x plus 1 is just going to stay the way it is. Now I have my inequality is greater than or equal to 0. So what I want to do is find the values of x at which any factor within this expression is 0. Because that will be like the cutoffs of where possible transitions between the part of the number line that holds the values of x that make this inequality true and those that don't. So when I look at this, I want to think, okay, each factor, what value of x makes x minus 2 equal to 0? Well, if I add 2 to both sides, I get that happens when x is 2. Then what value of x makes x minus 3 equal to 0? We'll add 3 to both sides. That's true when x is equal to 3. And what value of x makes x plus 1 equal to 0? Subtract 1 from both sides, I get when x is equal to negative 1. Now here we have to be very careful about this last one, because this expression was from the denominator of a fraction. And I can never allow my solution set to include values of x that would have the denominator be equal to 0, because that expression would be undefined. So even if this has an or equal to in its inequality, I still have to make sure not to include any values of x that would make the denominator 0. It's not in the domain of the expression. So what I'm going to do next is I'm going to draw my number line. And we have our 0, 1, 2, 3, 4, and negative 1, negative 2. And I just made sure that when I noted these values, they included the values that had their transition points. So I have a value of 2, where it might be a transition between those solutions and those parts of the number line that aren't solutions, at x equal 3, and at x equal negative 1. Now because negative 1 makes the denominator 0, I want to make sure that I do not include that cutoff. Remember, it's because it makes the denominator 0. x equal 2 makes the numerator 0 but not the denominator, and I'm supposed to include the values of x that make the expression 0. So I will include 2. And the same is true for x equal 3, so I will include 3. Now, next what we want to do is to remember that these transition points are places where it cuts the number line, where I want to test values of x that are left of the leftmost transition point, between each set, and right of the rightmost. So left of the leftmost, let's test, for example, any number left of -1 on the number line. So let's just test x equal -2. Well, -2 minus 2 is -4. -2 minus 3 is -5. So I have -4 times -5, which is positive 20 in the numerator. And then -2 plus 1 is -1. So when I look at 20 divided by -1, that's -20. So this value would be negative if I put in -2. And I don't want this expression to be negative for this specific example, because I want this side to come out greater than or equal to 0. Okay? So that's not going to work. I want numbers that would give me a positive expression over here. Next, we're going to plug in a value of x between -1 and 2. So let's test x equals 0. Well, 0 minus 2 is -2. 0 minus 3 is -3. And 0 plus 1 is 1. So when I carry that out, -2 times -3 is positive 6, and 6 divided by 1 is positive 6, a positive number. So my test gave me a positive value for this, which is what we want for this example, and the test value came from this span, so all the x values in that region will also give me out a positive value for that ratio. So we do want to have that set on the number line. Now I can kind of put up what I need to do on the test endpoints of that span. I don't include -1, so I'll put a parenthesis there, but I do include 2, so I'll put a bracket there. Okay, let's continue on with the rest of the regions. Let's test a number between 2 and 3, say 2.5. Okay, so 2.5 subtract 2 is going to give me a positive 0.5. 2.5 subtract 3 is a negative 0.5. 2.5 plus 1 is 3.5. And if I just think of the signs, because that really tells me about what I need in terms of my inequality, a positive times a negative is a negative, and a negative divided by a positive is a negative. So in the span of x's here, this would come out to be negative, and remember, for this particular problem, I want this side to be greater than or equal to 0. So that's not going to work. And now we're going to test a number greater than 3. So let's test x equal 4. So putting in 4 for our x's, I have 4 subtract 2 is 2. 4 subtract 3 is 1. And 4 plus 1 is 5. And 2 times 1 is 2, divided by 5 is positive 2/5, a positive number, and I want this to come out greater than or equal to 0, a positive number. So that also works. So I'll shade that region. And then again, remember that I want to include x equals 3, so I'll put a bracket and face it towards the shading. And that was the last test region to look at. So this graph is our final solution, the graph of the solution set to that inequality. If again, in this problem, they asked us to give the interval notation for it, I would have no graph down here. Here's where the solution set starts. So I'll have a parenthesis, -1, comma, 2 with the bracket. And then I don't use this, but I do want to make sure to pick up the next part of the solution. So we'll put a union symbol between those pieces of the solution set, and then go bracket at 3, comma, and then it points forever to the right, which means off to infinity. So, comma, infinity. Now remember, when you have a piece of your interval or an interval notation that includes an infinity going forever right, or if you had it where you needed to start with like a negative infinity coming from forever left, you put parentheses where the infinities are, because that's not a specific numerical value that you would include or not include. It's the idea of all the values continuing on in that manner will also work. So here's our interval notation for the solution set of that inequality, and here is our graph for the solution set of that inequality.